So this is going to be a time to try to, this morning and through lunch and then in our wrap-up to try to assess all that we've heard and try to think about what's going to come in the coming months and beyond. In this session, this first session this morning, we are going to hear again a bit more about what's going on in our ecosystem, and we're going to be focusing on federations, and we want to be thinking about how we can kind of build on top of those federations, connect to what they're doing. And we're going to start with Bob Hanisch, who's the director of the Virtual Astronomical Observatory project, to talk about a federation in astronomy.
All right, good morning. Yeah, I'm actually co-opted my talk here to wear another hat as well, which is the one I'll be wearing in about a month and a half time when I go to the National Institute of Standards and Technology. So I'll insert a few things about that as well, but primarily I'll be talking about the Virtual Observatory. So data in astronomy comes in many flavors, in many varieties. There are something of order 70 major data centers and observatories around the world that have substantial online data holdings, and something like 10,000 different data resources where a resource can be an archive, a complete archive, or it can be a catalog. We're very generic in how we describe resources. These data centers host anywhere from tens to hundreds of terabytes of data. Of course, in the future, they'll be much larger than that. I estimate there's at least 2 petabytes of astronomy data online nowadays. It may well be more than that. And the interesting thing is the growth rate is high, but the retrieval rate is very high as well. This data is repurposed very frequently, especially those data that are in archives that are well calibrated, well documented, and well tagged with metadata so that people can understand how to repurpose the data. In the future, we're going to see large surveys and new telescopes that will increase data rates to petabytes per day. Many people use the Large Synoptic Survey Telescope as sort of a benchmark here. And there's this interesting quotation from Tony Tyson, who said for LSST, the telescope is a peripheral to the data system. And this is indeed the right way to think about things in the future, that you run an experiment, the data collection entity is only one part of the entire system by which you're producing data and understanding that data to do science and to achieve knowledge. So how do we find our way through all of this? Enter the Virtual Observatory. The VO is a data discovery, access, and integration facility. It handles the diverse data types that we have in astronomy: images, spectra, time series, catalogs, databases, transient event notices. It's also an environment in which we have developed software and services that interact with each other through application intercommunication capabilities. We manage distributed computing through authentication, authorization, and process management services. And we work globally through the International Virtual Observatory Alliance, the IVOA, which has 21 members currently. The processes that are used in the IVOA are patterned on the W3C in terms of how we come up with proposed standards that go through a recommendation process and ultimately become globally accepted standards. The Virtual Observatory capabilities include data exchange, interoperability, and access to multi-wavelength data. Some of the key technologies here are in our data access layer: a simple image access protocol, simple spectral access protocol, and so forth. We also can query and cross-match tabular data, catalog data in distributed databases. We have a very simple protocol called the cone search, which simply says, tell me anything you know within a certain radius of a certain position on the sky, which is a very long skinny cone subtended from your eyeball. So that's why it's called a cone search. And the table access protocol, which is a much more generic way of querying databases, determining the database schema, and posing queries against that schema, and then actually cross-matching between distributed databases. We have capabilities for managing remote access to centralized computing and data storage. The standard here is called VO Space, which is supported by a single sign-on capability. And we have an application layered on this called SciDrive, which I'll show you a little bit more about in a few minutes. We also have the VO Event protocol, which encodes transient event notices. And we're planning to scale this up to the level that will be needed for the LSST transient events, which is maybe as much as 1 million messages per night. And then we also do data mining, characterization, classification, statistical analysis through applications that have been developed by groups in the Virtual Observatory in the IVOA. The architecture of the VO looks like this. At the top is the user layer, at the bottom is the resource layer, and then down the sides are the finding capabilities and the getting capabilities. Finding is discovery, getting is how do you actually get the results back once you find something of interest. This gets filled in here with, on the finding side, something called the Registry, which is basically the yellow pages of astronomical resources around the world. And then the various data access protocols are used once you identify resources that are of potential interest to you to actually home in on those data products that meet your specific interests and requirements. This is filled in by a quite extensive suite of standards and protocols. And there will be a quiz on what these all mean at the end of the talk. No, you don't have to memorize these, but over the now nearly 14 years that we've been working on developments in the Virtual Observatory framework, we have fleshed out increasingly sophisticated methods for doing discovery and access through these different layers and interfaces. And it looks quite complicated, but in fact all of these things do tie together in what is actually a quite organized way. And you don't have to know all of these standards in order to actually participate in the Virtual Observatory. You can put up a quite simple service such as a cone search or a simple image access service in a matter of hours or perhaps a day to wrap your data collection. So I wanted to talk a little bit more about the registry, which is really the key to data discovery in the VO. The registry is used to discover and locate resources, which are data and services that can be utilized in a VO application. And a resource here is basically anything that is describable and identifiable. It's data services, it's organizations, projects, software, the standards themselves. Basically anything that you can wrap some metadata description around is a resource. And so the registry contains a list of these resource descriptions expressed as structured metadata in XML. There are APIs that are used to access the data in the registry, and the core of the metadata definitions comes from Dublin Core, but we extended Dublin Core to include metadata terms that are more specific to astronomy resources. The registry utilizes the OAI PMH, which was talked about yesterday, for synchronizing and harvesting data from different types of registries. We have publishing registries where an organization that has many different resources can have an instance of a registry in which they aggregate all of the metadata about their resources, and then they allow that metadata to be harvested into a full searchable registry, which is the one that provides the APIs and the interactive access for applications. We have several full searchable registries in the international VO context. They are kept synchronized through the OAI PMH protocol so that all these data records are replicated and you can find the same resources whether you go to a registry that we operate in the US VAO or in the European VO or in the Japan VO or whatever. And then applications, as I say, use an API, which is a RESTful interface in order to dynamically query the registry and find resources that are of interest to an astronomer. This is just an example of what data discovery looks like in one of our tools that we've developed in the VAO. Most all of our data discovery searches are based on a position in the sky. The nice thing about astronomy is that things are there in some particular place. Solar system objects are the exception. They move around. So we don't handle moving objects nearly as well as we do objects that are static in their position on the sky. But also, astronomers have many different names for objects. And so the way that we do discovery is you type in an object name. We go through a service called a name resolver, which turns that name into position on the sky. And often an object will have dozens, if not 100 or more names, depending on the context in which that object is being described. But it has a unique position on the sky. And then we use that position to do a search, a dynamic search, against all of these resources that may have data. And the result is a list of resources. And then you have facets on the side here where you can down select according to the type of data you're interested in, images, spectra, where the data is hosted, and all sorts of attributes like that. You can also drill down into a particular data collection, and then what you see on the right here is footprints of where the images in that data collection actually are oriented on the sky. So you can figure out which of those many observations are actually covering the region of particular interest to you, and then download those data sets for local analysis, or you can automatically have them loaded into a web-based visualization tool such as the one here, or such as Aladdin, which comes from the CDS in Strasbourg, or other visualization tools. SciDrive is what I would call astro-centric cloud storage. This is a system developed at Johns Hopkins University based on the VO space standard. It basically functions like Dropbox. You can drag and drop data files into your SciDrive area. And then it also has the capability of automatically extracting metadata from the data sets that are dropped into your storage area. We can do this currently for tabular data and for FITS tables. There's also the idea to extract metadata from image headers so that you could automatically publish anything you put into your SciDrive area and have it discoverable by the appropriate VO standard protocols. That's not quite there yet, but that is something that we're hoping to do. This allows you to control data sharing amongst your colleagues. If you have a research team, you want to share data, you can do that. It uses our single sign-on mechanism, and it's also deployable as a virtual machine at other organizations, so you can have multiple instances of SciDrive that are communicating with each other, and you can copy data from one SciDrive instance to another. And I think, Rick, don't you have a SciDrive installed now, or will have soon? Dimitri, yeah, is now with you. Yeah. The guy who developed this at Johns Hopkins is now at San Diego. The VO concept is not unique to astronomy. We see virtual observatories in many different disciplines now. Space science in particular has virtual observatories in many of its subdiscipline areas. There's also the Virtual Solar Observatory, the Planetary Science Virtual Observatory, the Deep Carbon Virtual Observatory, which we heard a bit about yesterday. And just recently, I attended a meeting sponsored by the Kavli Foundation and General Electric Corporation in the UK, about 25 neuroscientists trying to come to grips with how they're going to manage their distributed data collections coming from the BRAIN project in Europe and the BRAIN initiative here in the US. And the synthesis of that meeting was that they should create the Virtual Brain Observatory, which I thought was a pretty cool thing to, they drank the Kool-Aid, you know, in terms of buying into the VO concept. I want to just change gears a little bit here and talk about what I'll be doing at NIST, the National Institute of Standards and Technology. At the end of July, I'll be moving there as director of the Office of Data and Informatics in the Material Measurement Laboratory. The MML deals with research and standards development in material science, chemistry, and biology, and is also the home for the Materials Genome Initiative, which again was mentioned a bit yesterday. I see my goal there is to really bring about a culture change. So I think I have a tall order in front of me. NIST does a fantastic job of producing sort of gold standard databases and publishing those through websites. But they also have a culture of bench scientists, PIs, who go into their laboratories, cobble together experiments, and produce data that is not very well documented. And a year or two later, they come back and try to understand what they did, and they didn't write down the conditions under which the data was obtained. And so it has very little or marginal value because those parameters are really important. So there's an inward-looking challenge in terms of providing tools, support, advice, common platforms, being a solution broker so that the internal data management is done in a much more comprehensive and thoughtful way. There are big data problems at NIST, but really there are lots of small and medium data problems, and I think generally those are the harder ones to solve because the metadata issues are much more complicated and much less homogeneous. There are also outward-looking challenges in terms of understanding all of the different services that NIST provides. NIST works in a very strict IT security environment because they are the standard bearer for the country in terms of IT security. And the way that many of the groups at NIST have dealt with this is to work outside the system because it's too hard to work inside the system. So if you go to NIST looking for data, there are something like, I found about 40 different top-level URLs where NIST data is available, and there's nothing that integrates them together. There is nist.gov/data, but people don't put things there because the rules for getting things in there are too difficult. So either I will help to change the rules, which may be a hopeless thing to do, or at least provide some way of organizing this information so you can go to one website and find out what exists at NIST across the board. I think we also need to work on understanding what the communities want from NIST. There's very little interaction in a formal sense between NIST and the user communities that it serves, and so I think that needs to be changed as well. NIST is a standards organization. It seems to me it ought to be in the game of defining standards, best practices for metadata management, for data storage, and so forth. And I think there are also many opportunities for collaboration with other government agencies, universities, and domain repositories. This is just a blurb on the Materials Genome Initiative describing the overall goals. And NIST is working to build the materials innovation infrastructure in support of the MGI, and there is a NIST website about MGI. So this is, again, part of the Material Measurement Lab. Jim Warren, my colleague, future colleague there, is the guy in charge of this. So I was asked to address a couple specific points regarding the National Data Service. The first one was about domain repositories. Of course, domain repositories are discipline specific. That's a bit of a tautology, but nevertheless, you get the point. There are various business models in use, but long-term sustainability is a major challenge. Margaret made this point very clearly yesterday. And I just want to refer you all to this white paper that came out of a workshop that was held last summer at the University of Michigan. Carol Ember from Yale and myself edited this document with inputs from many of the participants there, Margaret included. And rather than writing down that URL, if you just Google sustaining domain repositories, I think that's the first hit that comes back. It examines the various models, business models that are currently in use, and it also makes some recommendations about what we think were the most viable business models for going forward, including something we call the infrastructure model. Potential NDS roles here are in terms of customizing data management and curation tools that are built on a common substrate, providing access to cloud-like storage, but not at commercial cloud storage rates, which really have an impediment in terms of input and output. Perhaps a directory of ontology building and metadata management tools, a directory of domain repositories, perhaps providing accreditation services, and certainly providing advice, referral services, and something like the Genius Bar to help organizations who have data but don't know quite how to provide it in the most general way. In terms of technologies and standards to build on, well, just use the VO, right? And I said, sure, all right, you're not going to do that. This is the NIH syndrome, which is not the National Institutes of Health, but the not invented here. Nevertheless, I think there's much to be learned from what we've done in the VO and much to be learned from what others have done in building distributed data management and discovery systems. So we should look at these, understand their architectures, understand which components of their software stacks are reusable, and including things like generic collection level metadata. There's much that could be used here in common across various disciplines. I think crosstalk with RDA is important, and its major members, ANDS and EUDAT. The working groups and interest groups I listed here have obvious connection to what we are identifying as the goals for the NDS. And of course, there are a number of other extant archive services and metadata management systems, Dataverse, Dryad, iRods, DSpace, and many others that you're all familiar with, where I don't think NDS should try to replicate these capabilities, but should grow on top of these things. All of these services need to coexist, and we need to take advantage of them. Lessons learned regarding federation. First, it takes more time than you think. Community consensus requires buy-in early and throughout. Top-down imposition of standards is likely to fail. Scientists are cats, they do not like to be herded. We need to balance requirements coming from a research-oriented community with innovation in information technology. If you get IT innovation out in front too far, you will likely spend time building things that the research community doesn't really want. They'll be cool, but they won't be of interest to the research community. Marketing is very important. Scientists are generally not very good at marketing, but we need to manage expectations. Build it, well, they might come, they might not. So this is an important component. Coordination at the international level is essential. It takes time and effort, but it's important. Data models, sometimes they're obvious, more often they're not, but good data models inform the way that you build standards, and attention needs to be paid. And metadata collection and curation are eternal but essential tasks, and you should not underestimate the effort needed. I just want to close with a lesson learned that came to light when I was at this Kavli Foundation meeting a few weeks ago. Andy von Eschenbach, who was the head of the National Cancer Institute and also the commissioner of the FDA, actually started a program called CA-BIG, Cancer Biomedical Informatics Grid. This was funded at $350 million. It was deemed to be a failure. Its goal was to provide shared computing for biomedical research. The program, this is from an article that was published in Information Week a couple years ago, and is a summary of the results of a review panel that looked at this project. The program grew too rapidly without careful prioritization or a cost-effective business model. The software is over-designed, difficult to use, and lacking support and documentation. And the failure to link the mission objectives to the technology shows how important user acceptance and buy-in can be. So let's not spend $350 million doing something that the customers don't want. Let's take history to heart and do things in a way that embrace the customer, embrace the technology we have at hand, and do something useful. Thank you.